Hey students, today we're going to talk about tool design for joining processes. So we've talked about a bunch of other kinds of tool design so far, and joining processes are kind of different because we have to hold different components in the right position so that they can be joined together. So sometimes it becomes a little more complicated because we have these multiple parts, and so stack-ups can get really hard if you have to do super high precision joining. If you don't have to do as high a precision joining, one thing that you often have to do is deal with materials that aren't quite as rigid because they are not joined together. Once they're joined together, they will be very rigid, but in their previous condition they aren't. And then we also have to deal with specific process considerations that may come from that. Glue ooze or heating from and thermal expansion from welding, or chips and tool access if it's a mechanical type. So anyway, let's jump right into it. There we go. So there are primarily these two classes of joining. The first is the physical, and so that is a bond that is on contact surfaces. So this could be an adhesive or it could be welding, but it is some bonding agent occurring between two surfaces. It could also be brazing or soldering as well. The second class is mechanical, and so that is you positioning the two parts but then using an extra part to hold them together, and that extra part could be a screw or a bolt or a rivet, all kinds of things, but the two parts remain distinct from each other. So the differences as far as the purpose of the joint, a physical joint is generally a pretty permanent joint, or else it is at least very difficult to get it to come loose, but it is often a much more rigid joint. A mechanical joint is nice because it's often a joint that can be removed so that there can be repair done, or recycling becomes easier at end of life, things like that. But it is not nearly as strong typically because it is being joined at discrete fastener locations. And so immediately right off, when you think of these two, you can think of some differences between those. A physical join is going to require a fixture that allows us to get to an entire edge, whereas a mechanical join is going to be discrete points where we have to be able to get to it. And so that will be different. The physical bond often requires that the part be held both before and after the joining process takes place, so that an adhesive can cure or so that a weld can cool. Whereas the mechanical, as soon as you're done with that joint, you're done joining those two together, you can take it right out of the fixture immediately. So still, like other fixtures that we have been talking about, it is really important that the fixtures be able to locate the parts for the joining process. You have to support the parts. As I said, often they're floppier before they're joined together, so there is an assumption that the joining together is going to give them strength. So at this point they may be really floppy and hard to deal with. You have to allow access for whatever tools have to get in there, and you can't impart stresses on or deflections onto the part. And so it is important to be able to deal with whatever loads are being put on the part in the fixture. So this is readily apparent in welding fixtures where there's a bunch of thermal expansion that takes place. And so as you run that weld bead, that edge of the part or whatever you're welding will be getting considerably longer. And if you have it clamped so hard in the fixture that is being created, then they will warp out to the side if they're being held tightly enough, and that will cause the part to end up with a warped shape to it. And so it's really important to not induce stresses in there. I skipped, it has to be easy to load and unload. And so we're going to do a number of different designs for each of the different types of joining processes when we have our in-class portion. online, and one of the things that you're going to find is that loading and unloading the fixture is by far one of the hardest things to do. Because if you think of a fixture that holds these two parts together really well, and if these are big parts and you hold them together really well, then while it was easy to take these two parts and slip them in, now to get them out, either one part of the fixture has to collapse, or you have to lift the whole thing out of the top or slide it out, and now it's this big structure. Often the big structure is still kind of wobbly because you have to put it in for another assembly operation maybe. And so loading and unloading is really complex, and so that is often one of the biggest challenges that is there. And then anything for the specific process, so not damaging the part if it's pre-painted, dealing with chips, dealing with glue over squeeze, you know, all kinds of things like that, dealing with the heat that's in welding. Those are all really important to understand. So as we go through things, we're going to look at this set of characteristics. We're going to talk about how, you know, how does it locate, how does it support, what access does it provide, how about loading and unloading, how about imparting stress, and anything that's specific to the process. Okay, so the mechanical joining, again, is where we're doing these individual positions along the edge. And so it may require us to apply fasteners. And so applying fasteners often takes a lot more room than just something like putting in a glue joint. It may have multiple processes, so it often involves a center drill or a center punch to start off. Then there would be a drilling process. There might be a reaming process to get it to the right size. There might be drilling and tapping, or tapping as well, depending on whether on how it's done, whether there's a nut. Sometimes it will require access from both sides because you have to be able to put a screw in and a nut on the other side, possibly washers, so that will take a lot more area if you have to be able to put washers in place and then hold them there while you put things on. And so I have included two items here. This is a pneumatic drill, and so, you know, you can see that that's sort of handheld size, so it's not super large, but if you're trying to position things really tightly, then this chuck is a pretty big item to have to clear. You know, it's chucks are usually about 1.5 inches in diameter on the larger part of the chuck, and of course you can have bigger and smaller chucks. This on the right side is a rivet gun, and so if you're putting in rivets, this is for pulled rivets. This gun has about a 3/4 inch nozzle on it, but you can see that the gun is really large overall. This down here is for collecting the center studs that get pulled out of the rivet when it is pulled together to squeeze the two pieces of metal together. And then on the back it has this muffler to let out the exhaust stream from the compressed air and to let it out over a big area so it doesn't blow in your eye and blow chips in your eye. But these are pretty large. You know, this 3/4 inch diameter is one thing, that's kind of large, but my goodness, if you have to build something where you can get, you know, you can deal with this giant end of the rivet gun being somewhere, and both of these are pneumatic, so they also require a pneumatic hose coming off to the side, and so there's quite a bit there. Okay, so what would be important considerations for mechanical joining fixtures? Well, certainly the stability of the parts. If I am putting them together and then I'm having to push on it hard enough to drill a hole through something like steel, I have to be supporting those parts really, really well. I can't have the parts sliding from side to side. Access to that area for these tools. The ergonomics. So if I'm working on a tall sheet and some of it I'm having to work up above my head, that makes my hand go off the camera, sorry. Yeah, if I'm having to drill way up above my head, then I'm having to drill way down by my feet. that's certainly going to affect the person. And so a better fixture might be laid out horizontally. But one of the things that you'll find is that often when you put things out horizontally, first they take up a tremendous amount of room. But secondly, you can also get to the point where they're much harder to unload when they're horizontal, and harder to support because you don't have gravity helping you. We will also need to have some force and load capability so that we can put a fair amount of load on something. If you have drilled or tapped steel, it takes being able to apply a fairly good load so that you can go slowly and get that drill to go in there. You might also want something that would guide the tool, and so that would be a great thing for your fixture to have, would be little bushings on it, so that as somebody is putting these holes in, they don't have to center drill. They can just use a bushing and guide the drill at each point all the way down. And then you probably need a way to deal with the chips. So you can't have chips falling down where when you pull the part off the fixture, it's going to scratch all the paint. You can't have chips getting caught in between the joint and holding it so that the two surfaces don't mate together very well. You also can't have chips that are just getting into things so that the next time you clamp something up, there are chips already there and it doesn't position the parts correctly. All right. So I wanted to remind you of two DFM rules for assembly that are really critical when you're thinking about the design of these fixtures. So rule number 8 is you begin with the base component, so often the biggest or heaviest component, and a low center of gravity so that it's not going to be falling over all the time, or you're also not lifting something up and putting it in a precarious position. And then you're going to start adding parts to it. And assembly should proceed vertically, ideally, with the other parts added, and use gravity to hold them in place. Now, that is the fastest way, if you can do that, if you can put it there and have gravity hold it in place. One thing that we'll often find in fixtures is that we have to have more precision and more location than we can depend on gravity to provide, especially if we're not completely sure that our incoming materials are exactly flat every time. And so we may need to clamp against locators and not only depend on gravity. But it is much easier if you can take a big sheet of something and slide it in and have gravity hold it in place while you clamp it up, rather than having something where you're having to hold it against gravity with one hand while you clamp it with the other hand. That is a much harder fixture to load. Rule number 9 is that threaded fasteners are rubbish. They're time-consuming to assemble and difficult to automate. So you may want to use something else, snap fit, or something that is a much faster technique, something like rivets also. Now this is somewhat true and somewhat untrue, right? For the initial assembly, it is absolutely true that screws are very slow, because to bring something together, you know, a small amount with a screw means that the screw has to rotate many, many times, and it typically has to rotate starting before it gets to the point where it's drawing the two together, and then it has to rotate afterwards. And then for the fastener to have full strength, you want to have at least 1.5 to 3 threads sticking out on the other side. And so those are kind of wasted threads, but they're important to know that you've put the screw through far enough, and you have to have enough length that you're supporting across multiple threads. So that you are spreading the load across multiple threads. So anyway, all that to say, threads are slow. Some ways to deal with that is, if you have to use threads, if you can use a higher pitch count thread, or a more coarse thread would be a better way to say it. So if you can use you know, an 824 rather than an 832, so that's 24 threads per inch rather than 32 threads per inch. That will go in much faster. The flip side to that is that an 824 screw does not have the same load capability as an 832, because the threads with that coarser pitch are also deeper, and so there is less shaft diameter that is supporting that load. And so that's always a balance. All right, so threaded fasteners are rubbish. Why are they used all the time? Well, they're used all the time because they allow for things to be taken apart. And so that is a real value. And so sometimes the DFM rules for assembly get overridden by the design requirements and other things that we have, other needs. So what I want to do right now is I want to just look at a fixture, and I want to try to look at this fixture thinking about our set of characteristics. So if you look at this, this is the tail section of a plane, and there are two of them, and you can see that this is a really big fixture, right? You can walk around this fixture, you can move all over. The fixture is 28.5 feet by 6.5 feet by 14 feet, so that's a big fixture. The positioning accuracy on this thing is 5/1000ths of an inch, so that is a little over the thickness of a sheet of paper. So big parts, but it's got to be in exactly the right place. So I use a laser tracker to confirm the fixture points. We'll talk about laser trackers a little bit later, maybe not right now. But anyway, it's just a way of getting some fairly precise locations at a big distance. And it has to be straight and square. So when you look at this structure, what do you think was important to the assembly process for parts made on this structure? And we can think about our list of supporting and locating and access and the tools. We don't know exactly what's happening in this assembly jig. They might be putting some ribs inside this fuselage. They might be putting wire looms in here. Maybe they're assembling that back door on it. I don't know exactly what it was. So what do you think might be important? Well, as I look at it, I think that certainly ergonomics is important, because you see that this fixture, which could be relatively simple maybe for supporting these two sides, is a massive fixture, and most of that huge size is because it has a bunch of ways to get people to different levels and different sides of these two items. And so there seems to be a lot of consideration of ergonomics and access of the operators to this fixture. I think also, to me, when I look at this, it says that the parts needed a tremendous amount of support. They may not be able to support themselves very well. And the reason that I think that is, this is not that big a piece, and if it's an aircraft piece, it probably doesn't weigh all that much really. And these beams that it's connected to are huge. And so what I think those big beams mean is that they needed a really rigid structure to clamp this thing or hold this thing against, so that they would be able to support it really well. Other things that we look at, if we look, it has a lot of access. These are pretty big holes that are open here, so it has a lot of access capability. So they've done a lot of work to be able to get in there. Now, one of the interesting things about this fixture is that we don't have enough detail to know how they're actually holding the parts in place, and that would be really interesting to know on this fixture. So you can potentially think of other ideas that may have been really important to this. Let me make sure I didn't have any others that I wanted to mention. Yeah, I think that's probably good for right now. Okay. So what innovative ideas do you notice in this fixture? Are there any that you see there? When I look at it, there are a couple things that are interesting. Notice how there's this fixture, but the fixture is made in sections, and so it looks like those sections could come apart maybe to be able to move something out of the middle and join the two halves together, possibly. There are leveling feet on the really big sections, but the really big things that are supporting the part seem to be somewhat independent of the walkways for the people. So it may be at least the walkways for the people can be taken away. so that loading and unloading of the structure is easier. Yeah. So let's, this is actually by the same company. I was just have searched over time and found some interesting examples on the web. And so just wanted to look at these. All right, so this is a smaller assembly fixture. It is 12.5 feet long, 6 feet wide, and 2.5 feet to the center line in height. Dimensional positioning again of 0.005. And you can see that it has these ribs that go across, and so something is getting laid on these ribs, laid upon the ribs, and then there are clamps. Each of these red-handled things is just a toggle clamp to be able to clamp something in place. And so I would ask with this one, similar to the last, what ways do you think the material choices match the fixture requirements here? So what can we tell about this fixture by what we have here? Well, some things that I think we would see is it appears that this is made of aluminum, at least by color. It looks like aluminum. So there was some effort to make this light. And you can see that there's a black strip here, and then there's one down here as well. It looks like there are some white strips in here as well, maybe. It's a little hard to see, I understand. But to me, those look like different materials, plastic materials, maybe HDPE or Teflons or just other materials to protect whatever is being put on here from getting scratched on the surface. The fixture is all manually operated. It's all hand toggle clamps. There isn't any power on it. There's a hand wheel down here to turn the fixture. And so I think that says sort of what the value of the component is. If the component is really expensive and you really need to, then you can automate it. But if you don't have to automate it, or if the component is not worth quite as much money, then you would make the fixture be worth less money too and make it all be manually operated. So I think that says something. What do we think was important about the assembly process? Well, when I look at it, one of the things that I think is, look at the number of ribs that are on here and the number of clamps. It is clearly non-deterministic, right? There should be, we could approximate, it's an arc, but we could approximate it as a plane and say that it ought to contact in 3 points to be deterministic. Maybe if you want to say it's a plane plus you're preventing, 1 or 2 other degrees of freedom because it's an arc, maybe you're getting to 4 or 5 points of contact if you're really pushing things, but that's all. And this has, I don't know, it's hard to count because it's hard to see, but it looks like it has at least 20 different points of contact. Well, that tells us that the part itself is kind of floppy, and so it won't hold its shape correctly on its own. And so the structure has to provide that to the process. We can see that ergonomics was important because we have this hand wheel and it's on this cart, so we can rotate the part up to be able to work on it. We can rotate it the other way to be able to work on the back side. So it's really good for ergonomics to be able to get to whatever location on here we needed. And then one other thing is, it's pretty apparent to me that this part is going to have to be transferred while on this fixture. And so you can see that in a couple of locations, both for the fixture itself and then in this rotating table, there are weights written on the side. And so what that says to me is that they're going to have to be lifting this with either a crane or a fork truck. And so then you want to have the weights on the side so you never get there with the wrong size straps or the wrong fork truck and end up with somebody really getting hurt. And so that just says, and when I look at it, you can see also there are these big pins on the sides, clevises for hooking onto straps really quickly. So this is meant to be lifted and moved once the part is in place. So this is going to be assembled somewhere else as well. Okay, so that's enough for this video, talking about mechanical assembly processes and just ways that we can create fixtures. Like I said, when we get to class, we're going to be practicing this and trying to create some fixtures for a problem that I encountered a number of years ago. All right, see you in the next video or in class.